Hi everyone, welcome to this video on lesson 3 of the Earth and Climate scheme of work, which is on constructive plate boundaries. In the previous lesson, we introduced students to Wegener and his theory of continental drift. And what we're going to do is build upon that idea in today's lesson. And this is a kind of bridging lesson between the first couple, which are really introducing Earth science to students and giving them this idea that we can't see inside the Earth, but we can use the evidence that we've got from earthquakes, as we saw in the first lesson, and in the second lesson we saw evidence from rocks, from fossils, from dating of the crust. We're using this evidence to generate a picture of what it looks like inside the Earth. What we're going to do in this lesson is kind of bridge between that kind of idea of how Earth science works to looking at some of the more substantive matter of Earth science, which is the rock cycle and different types of rocks and so on. So this kind of bridges. And this one actually is the kind of lesson that they will probably do in geography as well. But it's really, really important, I think. And again, it's a lesson students find interesting. So what we can do first, and I've just sketched out a very rudimentary globe here, but what we can do first is just remind students of Wegener's theory of continental drift, this idea that he suggested the continents must be moving apart. So what we're going to do in today's lesson is zoom in on this kind of imaginary line down the middle of the Atlantic Ocean. Well, it's not actually imaginary, it's a real thing, which we call the Mid-Atlantic Ridge. And you can explain to students that we're going to look at the Mid-Atlantic Ridge, and in particular we're going to look at a country that lies on the Mid-Atlantic Ridge. It's a country I've never been to. I would absolutely love to go to because it looks just incredible, and that country is Iceland. So you can show them, and again, you don't need to draw this necessarily, but you can show them where that is on a map. It's up here somewhere. In fact, it's further north, isn't it? It's north of the UK, so let's draw a bit further up. But you can show them that we're going to focus, we're going to zoom in on Iceland up here, like this. And we might add a note to show that here, like that. And the reason I'm starting here is because I want to keep it relatively concrete. This is a picture students will be happy with. And we're going to start with concrete. Okay, here's the globe. Here's the middle of the Atlantic Ocean. This is where Iceland is, and so on. That's not too difficult for students to get their head around. What we're going to do now is zoom in on here. But we're not going to do our usual type of zoom in here. This is going to be a slightly different one because we're essentially going to take a cross section through the Earth, and you want to emphasize that to students. So it's like we're slicing through the Earth to look at what's going on at the Mid-Atlantic Ridge. So what we're going to do is draw the Earth again here. But this time, rather than zooming in, as we often do, we're taking a cross section. So inside here, I've got my core, and my inner core here, which I'll do a bit darker. I'll then shade this one to show that this is the outer core, like this. And then I've got the mantle in here and the crust on the outside. And you can maybe label here that the Mid-Atlantic Ridge would be found here. And again, because we're taking a cross section, this is kind of what it looks like. This is the Mid-Atlantic Ridge. So I'm progressively getting more abstract so that I'm not losing students immediately. Now, what we're going to talk about now is how it is that the Mid-Atlantic Ridge creates new crust. So the first thing we can talk about is the fact that, well, we can do a bit of prerequisite knowledge here that actually the core is really hot. So the further down you go, the hotter you get within the Earth. And what that means is that this mantle around here gets heated up. Now, students may not remember this from year 7, and that's kind of fine. It's up to you, depending on your group, because convection is a bit of a nightmare. It's up to you how much you want to revisit that and how much you just kind of want to tell them what happens without worrying too much about the details. But the point is, this mantle down near the core gets heated up, because this is the hottest and the core is much hotter. It gets heated up, and again, it becomes less dense, so it begins to rise. The main point is, because it's getting heated, it begins to rise. And students, even if they haven't got the ins and outs of convection, they should be relatively happy with that. So it starts to rise like this. Now, as it approaches the Earth's crust, which is obviously a lot cooler, it starts to cool off, as you might expect. And as it cools off, rather than, it doesn't just drop straight back down, it starts to move that way like this. And one thing I should have said, by the way, is that what we're talking about here happens over millions of years, because the mantle is a solid. It's essentially a solid. But the theory that we've got here, and this seems to be the best theory that explains the facts, the theory that we've got here is that over millions of years, even though it's a solid, it kind of behaves a little bit like a liquid. So it starts to move upwards, and then it comes across like this. And we can label this as a convection current inside the mantle. And the key point students need to recognize is it's these convection currents due to the heat from the center of the Earth. It's these convection currents that are really driving everything that's going on at the Earth's surface. Now, depending on your group, you may want to tell them, where is that energy coming from? Well, that energy is coming from all sorts of radioactive things happening inside the core. Things that we didn't know about a couple of hundred years ago, and actually it's only in the last century or so that we have that knowledge, and all of this stuff starts to make sense. Now what we can do next is zoom in again, so we're going to zoom in again here on what's going on here because of these convection currents. So I'm going to show students an even larger view of what's going on like this. And what I want to emphasize to them, hopefully that's clear on the video, what I want to emphasize to them is that if this is the crust here like this, if this is a section of crust like that, because of that mantle moving along, as it cools and starts to move sideways rather than rising up, as it starts to move sideways, it's being kind of displaced by the mantle moving up beneath it. So I can label the mantle moving in that direction like this, and in that direction like this. It sort of drags the crust with it. So you can label this as the crust being dragged along with it up above. The crust gets dragged along too. And what we can explain to students is that this opens up a gap. A gap opens up. Now this gap doesn't just remain empty. What happens here is that some magma comes up and it fills the gap. Some magma is just material from the mantle. So we can label this as magma from the mantle. Some hot magma comes up and fills the gap. But what's going to happen over time is that that magma is going to cool, it's going to solidify, and essentially that forms new crust. So over time what you see is the following. I'm going to try and draw this again and show this to students. You've still got these convection currents pulling the crust apart. So new gaps are being created. Now this magma that was here before, I'm going to choose a different colour if I have one. Yeah, maybe I'll do it in blue just to illustrate that it's cooled down. So let's show the mantle pulling the crust apart. You can show the crust is also moving still. And then we can explain to students that this magma, these layers, they get pulled apart too. They cool down and solidify, and they form new crust. But then a new gap is created, so more hot magma rises to fill it. So we've got the hot stuff in the middle and the cooler stuff on the outside. And you can label this as new crust, like that. So this is what's going on, and this is what we believe is happening. And I'll just move the camera down so you can see it like that. So this is all happening because of convection currents in the mantle, and the magma is rising up. It's cooling, it's solidifying, it's forming new crust. Again, you can choose how many of those words you want to add to your diagram, and how much you just want students to remember when they do the tasks and they write about this stuff later on in the lesson. The final thing to do is to kind of zoom back out. So if we just, I will literally zoom out with my camera here. So, okay, it's fine to say, well, this is what we think is going on. So if we take a cross section of the Earth around Iceland, we think there's these convection currents. We think the crust is being pulled apart, magma's rising, blah, 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 blah. Well, what would we expect to see if this was true? That's a really important question. Well, if you've got this magma kind of rising up and these gaps in the crust, well, you'd expect to see a couple of things. One is that the crust along the mid-Atlantic ridge is super, super new. And as you go further and further away from it, that crust gets older and older and older. And again, I mentioned this in the previous video. I think a visualizer is not the best way to explain this. So if you can find a video or some diagrams about the work that the US Navy did in terms of measuring the magnetic field direction and how that changes over time, and using that to work out an age of the seafloor, that's a really good resource to share. So we do have evidence that the crust gets older as you go further out, and that the newest crust lies close to the mid-Atlantic ridge. That's one thing. But something even more tangible is to say, well, if you're getting this kind of magma constantly rising up, would you not expect to get quite a few volcanoes and things like that in Iceland? And then you can show students videos of what it's like on Iceland. I mean, Iceland is just basically one big volcanic island. So actually, if we go from the concrete, looking at the whole globe, to looking at what's going on inside and looking at the crust in detail, we can then go back to the concrete and say, if this was true, we'd expect to see loads of volcanoes, and indeed we do. So this seems like a pretty good way of explaining what's going on. Now, this picture is really, really important. As I said before, this is the link between Wegener, continental drift, that's going to take us then to look at igneous rocks and some of the features of igneous rocks, which are, of course, formed by magma rising and cooling. And that's what we'll look at in the next lesson.